Hi everyone, this is the problem 2 long candlesticks from POI round 3 2018. This is from day 2. To summarize the problem, we are basically given two arrays. Essentially every element corresponds to a flavor and a length. So the flavor can be of two types. There is T for strawberry and W for vanilla, and then the length can be some integer. So for example, the first array is, let's say, T5, W7, T4. That means there is first 5 length of strawberry, then 7 length of vanilla, and then 5 length of strawberry. In the second array, it's also of length 3. Rather, there are 3 segments. The first segment is length 6 of vanilla, length 6 of strawberry, length 6 of vanilla again. Now, what do we have to report? We have to report the longest total length that we can form out of all the segments, so that the total length of strawberry and vanilla segments are same in both the arrays. So let's take this example. So the red portions represent T, that is strawberry, and then the purple portions represent vanilla. So we can take a segment like this, for example. So let's say this segment, and here let's say this segment. So what is the total length? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. The length of the both of the segments are same. So this is also 13 length, this is also 13 length. And the total length of strawberry and vanilla are also the same. How? Here there is 1, 2, 3, 4, 5, 6. Here there is 1, 2, 3, 4, 5, 6. And similarly, if you count the purple things, there is 1, 2, 3, 4, 5, 6, 7. And here there is 1, 2, 3, 4, 5, 6, 7. So the total amount of red and purple both match, and the maximum length that we can take is 13. Note that we cannot take any more, because if you take any more here, you will be increasing purple, but here you cannot increase purple anymore, so it's kind of maxed out already. So you have to find what is the largest length contiguous subs array that you can take in either places, so that total lengths are equal. Rather, total lengths of red and purple, or strawberry or vanilla, however you might want to say it, are equal. So let's look at the constraints for this problem. Here it is given that the total length of segment can get up to 10 to the power 9. So that is total length of all these segments. But the number of these segments is up to 1000. What does that mean? Well, it just means that this is a segment, this is a segment, and this is a segment. So these can be up to 1000 in length, right? But every one of these segments can have 10 to the power 6 elements in them. So that makes it 10 to the power 6 into 10 to the power 3 equal to 10 to the power 9. I mean, it's not given to be 10 to the power 6. I'm just giving it as an example. It might be that there is only one such cell and it contains 10 to the power 9 cells all by its own. So notice that the unique thing about the segments is that all of the elements here are of the same color. Segments are necessarily divided by the same color. So how do we approach this problem? Well, the first clue towards the solution here should be that the 10 to the power 3 things seems to be very small. So maybe it is possible for us to iterate somehow over, let's say, maybe the starting window here and the starting window here. So what do I mean by starting window? Well, where does my optimal range start at? correct? So let's say the segments are, and now I'll draw this as filled boxes. Just assume that there are multiple cells in each of these. So let's have a diagram of something like this. Now, one idea can be that let's say we fix that, okay, our whatever our suboptimal range is, maybe it starts from this zone in the first subarray, and maybe let's say it starts at this zone in the second subarray. Then what is the maximal place that we can go to? If we could find that in, let's say, order log n time, or like n max time, which is, just to remind you, 10 to the power 9, then maybe we can just try to brute over these things, and then maybe we can achieve an n log square n algorithm. But it turns out that it is hard to do this log n time thing. Like, it's hard to figure out till where can I stretch it, and it's not like we know that which exact place this initial thing is also going to start in, right? Because there's a range of things that it can start at. So what we can try to do is, we still want to take advantage of the fact that a possible n square thing might pass. We still have an opportunity to do something that is n square. Well, notice that these things can only be of two colors, and they continuously increase or decrease in a particular segment, right? So if you, let's say, think about a segment like this, if you shift the left pointer towards the left, the number of blue items will increase or decrease, but it will be a continuous thing. So instead of trying to make a pointer here and then make a pointer here and then try to traverse, let's try to take both of the pointers here and then figure out what we can do. So one thing that we can try here is that, let's say, if we say that, okay, the first pointer of our range will start in here and the second pointer will start here, that is basically we will cover some sub range like this, where this pointer might go left till this point and this to the right to this point, and same for this. What are the possible set of values that we can achieve? What are the possible set of red and blue values that we can achieve? Well, here obviously only the blue values change, right? But if we had a configuration like the following, and then there are some blue stuff here, there are some red stuff here, okay, there are multiple segments in between, and then there is a blue thing here, and let's say our range that we were considering spanned like this, then we definitely know that the number of red items, so the number of red items will be between some range LR comma, rather L red comma R red, correct? That is, L red will be reached when we start our segment from the rightmost point, and R red will be reached when we start it from here, correct? So these are the range of values that the red coefficient can take, and similarly for the blue thing. For the blue thing also, we can have blue that will range from some L blue to some R blue. Note that L and R is basically the number of blue items that we have in our range. So L blue corresponds to this portion, R blue corresponds to kind of this portion. So what do we do with this information? Well, once we extract this information for both of the arrays, we now have n square total pairs, or rather n square pairs for both the array A1 and the array A2, right? And these are not just pairs, these are kind of pairs of pairs, that is a range L to R of red values and a range L to R of blue values for every array that we have. So n square of these, n square of these. Now let's assume that there is a data structure that can answer this query. We can feed it a pair like this, and then from all the lists here it can find the largest x plus y such that, so let's say this is L1 R1, this is L2 R2. So L1 less than equal to x less than R1, L2 less than equal to y less than equal to R2, and there exists such let's say L3 R3 and L4 R4 here. So this corresponds to blue, this corresponds to, let's say, red, such that L3 less than equal to x less than equal to R3, L4 less than equal to y less than equal to R4, right? So these are also pairs, right? So if we had a data structure that could answer as the largest possible value of such x plus y, then we could have just queried for all of the ranges and then got this maximum x plus y value. Let's say we could have done it in log n time, then our total algorithm takes n log square n, rather n square log n time. So this seems very hard to do for a data structure, right? So let's give it a more visual approach. So what is this red blue pairs where red is also varying, blue is also varying? What does this look like in a 2D graph? It's basically like a rectangle. So the x-axis, let's say, represents the number of red points you have taken, and the y-axis the number of blue points you have taken. So you can think of each pair as the number of red and number of blue points that you have taken, right? So this is your x comma y things, these things, and it being inside the rectangle means that it satisfies these two conditions, correct? Like you can think of this region as L1 R1, like the x coordinates, and the y coordinates like this as L2 R2. Now what is this data structure essentially doing? This data structure itself has many of these rectangles, that is possible values of red and blue values, like combination of red and blue values, which are given by these L3 R3 L4 R4 pairs. It has many such rectangles. Let me do it another color. Right, and then when you give it a query rectangle, it finds you the largest point such that x plus y is maximized. It gives you the largest point such that it is also covered by a green square. Now this data structure itself might also be kind of hard to do, so we can do something else instead. Think of all the lists generated by A2 as these green colored rectangles, and think of all the lists, or rather all the pairs generated by A1 as red colored rectangles. Then we basically want to find the maximum value of x plus y such that x comma y is present at an intersection of a red and green rectangle, right? So x and y is covered by both red and green rectangles. Now maximizing x plus y might seem difficult, and you might think that there is another dimension of information that we are adding, but it's really not so, because we will only want to find the values when there is an ending line of a rectangle, or let's say a beginning line of a rectangle, or things like that. So as with many other rectangle problems, we try to do this using an offline sweep. So what do we do in the offline sweep? We have a line which is basically corresponding to x equal to c for some value of c, and we sweep this line over the xy plane, And there are some rectangles like this here, there are some rectangles like this here, and maybe some green rectangles like these. And we try to compute some information, but only at the points where there is a special event. So a special event qualifies as the beginning of a rectangle or an ending of a rectangle. Okay. So what we basically want to do is somehow store information appropriately so that when we reach such an event while doing the sweep line from left to right, we can efficiently say that for that particular value of x, what is the greatest value of y such that they are like x comma y is still covered by a red and a green rectangle. So turns out that we can answer this query pretty efficiently using two segment trees and binary search. So in one segment tree, it's basically like an identity array where the underlying array of the segment tree, let's say call this a of I equal to 1 if the coordinate x comma I is green at that point, and similarly we say that b of I is 1 when x comma I is red at that point. So notice that we are only maintaining the segment tree over one dimension, that is the yth dimension. As we move our line sweep, the x dimension is being taken care of by the sweep line and the y dimension is being taken care of by the segment tree. So what are we effectively trying to find? That is, for every x, the largest I such that a of I is also equal to 1 and b of I is also equal to 1. This is what we want to find. So instead of it being equal to 1, let me say that it is greater than 0 for both of the cases. How does this help? Well, this helps in maintaining the data structure because now our events just corresponds to, like, when we reach a beginning of a rectangle, we do a range update, a range plus 1. So let's say this is L and this is R. So in our segment tree, for the range L to R, we do a plus 1, and when we reach the ending point, we just do a range minus 1. That way, if a cell value is greater than 0, we know that there are one or maybe more than one green rectangle that cover that particular cell, and similarly for BI, it represents the number of red rectangles that covers a cell. This is still standard offline sweep on rectangles with segment trees. I'll link some example problems for learning this technique a bit more. Well, lastly, what we do, how do we find the largest such I? We just do a binary search. We do a binary search simultaneously on both the segment trees. We try to go right every time we see that, okay, the right portion has at least one value that is greater than 0 in both the array A and the array B. If there are no such values in the right child, then we go to the left child. That is how we do our binary search. Note that for the problem, at least in my implementation, my recursive binary search did not pass, so I have implemented it in an iterative way inside the segment tree. But the rest of the code is pretty simple. I am using a dynamic segment tree, that is one whose values are, or rather whose nodes are allocated at runtime, because notice here that the values of these i's or x or whatever coordinates can range from 1 to 10 to the power 9, right? So we cannot use our regular segment trees. So I use dynamic segment trees with lazy propagation, because notice that we have range updates here. So overall, memory complexity wise and time complexity wise, our solution becomes n squared log n. Why? Because we have n squared such rectangles. Actually, we have, to be more precise, 2 n squared such rectangles because we have two arrays. We do a sweep line from left to right. The sweep line takes care of our x value. For the y value, we maintain it using a segment tree. When we hit a left side or left edge of a rectangle, we do a range update of +1 from L to R, and then when we hit the right endpoint, we do a -1. We do this using, we can simulate this by storing events. It is pretty standard for a sweep line technique. The implementation for this problem is given below as well. You can check it out. It does get AC on the POI server as well. So we essentially reduced the problem to a sweep line geometric problem, and then we solved it using segment trees. Hope you like the solution. That's it for today. Thank you.